Hello students, in lecture 8 of your course Advanced Calculus and Special Functions, we study homogeneous function. What is a homogeneous function of more than one variable? Here we will start for the function of two variables, certain examples of the homogeneous function, then the Euler's theorem and proof of the Euler theorem regarding two variables, examples, and few exercises are given for a practice. So first we give the definition of a homogeneous function. A homogeneous function f of xy is said to be a function is said to be homogeneous of degree n if it can be expressed in the form x raised to power n f of y by x. Means you will have some power of x outside and the remaining part will be a function in the form of the variable y by x. Or alternately, you can also take some y power common outside this and you are left with the function of x by y. So alternately, another way to represent a homogeneous function is that if you replace x with tx and y with ty, then you will be able to take t raised to power n outside and the function will remain as such f of xy. In that situation, we'll say that this f of xy is a homogeneous function of degree n. So let us see one example here. Let f of xy is equal to x plus y divided by under root x plus under root y. Then you can write it as I'm taking x common from the numerator, then the numerator will become 1 plus y by x. Similarly, when we take x raised to power x under root of x outside, then we are left with this type of expression. So ultimately, how we can put it in this form, x raised to power n and or y raised to power n. So here we are taking powers of x outside. So when x raised to power 1 is there in numerator and x raised to power under root means x raised to power 1 by 2 in the denominator, then you take this on in the numerator, you are left with 1 minus 1 by 2. In fact, it remains x raised to power 1 by 2 and the remaining part in the numerator remain as such, and similarly in the denominator this part remain as such. Now you can look at this part of the function, this part of the expression. You can see the whole thing can be expressed as the whole thing in the form of the variable y by x. So that way this part can be written as f of y by x. This part can be written as f of y by x, and you have the power x raised to power 1 by 2. So you can see that this f of xy given here in this example is a homogeneous function. This is a homogeneous function of degree 1 by 2. This is a homogeneous function of degree 1 by 2. Now we take the second example here. Suppose we are taking this f of xy is equal to ax square plus 2hxy plus by square. Obviously, a, h and b are the constants here. X and y are the variables. So either you take x to the power something outside. So we should take the highest power of x, in fact. So when you take highest power of x outside this, then you are left with a here, and here when you take x square outside, that means you are dividing the whole expression by x square. When you divide it by x square, x goes with this, then for this part we are left with 2hy by x. When you are dividing it here by x square, so you get y by x square. So in fact, again you have obtained x raised to power some number here. For example, here this is 2, and the rest of the expression is in the form of variable y by x. So this whole expression within these square brackets can be written like this, f of xy. So in fact, this f of xy is a homogeneous function of degree 2 in this case. So this is second example. I'll come to the third example. Now, if we take u is equal to log of xy divided by x plus y under root. So now if we want to take x outside of this, then it is not possible here. So that is why we remove this log from this side. So when you remove log from this side, you take in the left hand side, it becomes the e raised to power u. and the right hand side becomes xy divided by x plus y under root. Now our aim is to make this part in the form so that x raised to power some number is on one side, and the rest of the part should be in the form of y by x. So how we can do this? So in fact, in this situation, it will be better if we multiply this with x and divide the numerator with x. It is not going to change anything, so that way we can write like this. Now in the denominator, we can take x outside of this under root. So in fact, it will be under root of x, and within this under root, if we look at the situation, we are left with, in fact, under root should be here 1 plus, in fact this is 1 plus y by x, 1 plus y by x. Now you simplify this, x square is there, this becomes x square, and here under root of x. And if you look at the remaining part, if you look at this remaining part, it is in fact in the form of the variable y by x. So this remaining part can be written as a function of y by x. So that is why here this e raised to power is equal to x square divided by under root x f of y by x. So this is x e raised to power u x raised to power 3 by 2 f of y by x. So here you can say that e raised to power u is a homogeneous function of degree 3 by 2. So in this particular example, the main point to be noted is that here u is not the homogeneous function, but e raised to power u becomes the homogeneous function of variables x and y, and its degree is 3 by 2. So similarly, you can have several examples. One, for example, in trigonometrically, if we look at certain situations, I can write here u equal to, suppose, sine inverse xy over x square plus y square. And if you are asked to find what is the, is this function is homogeneous or not, then in fact you will be not talking about the homogeneity of this function u. In fact, you should take this sine inverse on this side, so that it becomes sine u equal to xy over x square plus y square. So in that situation, you will talk about the homogeneity of this function sine u. Okay, so you can have several examples of this type where the given function u will not be homogeneous, but after changing its form, certain expression you simplify. For example, here you have simplified this logarithm, and here we have simplified this inverse function. So in this way, several examples can be there. So next is the Euler's theorem, an important result in the function of two variables, and in fact the function of several variables. This is a very simplified form. Here we are discussing, that is the homogeneous Euler's theorem for a homogeneous function of two variables whose degree is n. So statement of the theorem is like that: if u is a homogeneous function of degree n in the variables x and y, then the expression x del u by del x plus y del u over del y is equal to n into u. N is the degree of the homogeneous function. So you have to show that this expression will hold if you have a homogeneous function of degree n in terms of two variables x and y. So let's prove it. Since u is a homogeneous function of degree n in the variables x and y, then it can be expressed as u is equal to x raised to power n f of y by x. So this is obvious from the definition which we have discussed about the homogeneous function. So this is equation 1. Now we take the partial derivative with respect to x. Why we are taking partial derivative? Because we want to show that this expression in left hand side is equal to n into u. So in order to obtain the expression of the left hand side, first we have to take the partial derivative with respect to u, then we'll take the partial derivative with respect to y. Here partial derivative of u with respect to x, then partial derivative of u with respect to y. Then you will multiply this expression with x, then with y, and you will add these two, so that we shall see that it is equal to nu or not. Fine. So here u is this thing. Now you partially differentiate equation 1 with respect to x. So you have del u by del x is equal to c in the right hand side. The derivative of first function, you will apply the product rule here. Derivative of this is n into x raised to power n minus 1, and the second function is left as such. Plus, in the product rule, now the first function will be kept as such, and you will differentiate the second with respect to x, and of course y will be treated as constant because you are taking the partial derivative. So first function as such, then the derivative of this with respect to x, we have this is f dash y by x, and you will take the derivative of this part. So you'll say that this is equal to y, because it is constant, so derivative of 1 by x is in fact minus 1 by x square. So after simplification, we'll get del u by del x is equal to n into x to power n minus 1 f of y by x minus when this square goes here, it becomes x to power n minus 2, and this minus sign will be there, f dash y by x. Further simplification gives you the second equation. When you multiply this equation with x you are multiplying here, then x here throughout in this part, so you get this equation 2. Exactly in the same manner, we can obtain del u by del y. Del u by del y means the partial derivative of u with respect to y. So when you are differentiating with respect to y, then of course this x will be treated as constant. So x is to power n as such f dash y by x, and derivative of this with respect to y gives you 1 by x. So after simplification, del u by del y is equal to this quantity. When you multiply with y on both sides, so you get this quantity. So now this is equation number 3. Now adding equations 2 and 3, we get x del u by del x, y del u over del y, means in left hand side you get this quantity, in right hand side you will add this part here, this part plus this part here. So finally you will obtain n into x raised to power n f of y by x. But you know from equation 1 that x raised to power n into f of y by x is in fact equal to u. So we have obtained that x into del u by del x plus y into del u over del y is equal to n into u. So this proves the Euler's theorem. Now if we want to extend this Euler's theorem for a function of suppose 3 variables, suppose you have that u is a function of x, y and z, then you can write that x del u by del x plus y del u by del y plus z del u by del z equal to n into u. So in this way you can extend this theorem to as many variables as desired. So this is the Euler theorem. Then one more result related to Euler theorem is here. If u is a homogeneous function of degree n in the variables x and y, then we have x square into del square u over del x square plus 2xy del square u over del x del y plus y square del square u by del y square is equal to n into n minus 1 u. So we can prove this result with the help of Euler theorem, because in the statement we are given that u is a homogeneous function of degree n. So when u is a homogeneous function of degree n, then directly from the Euler's theorem we can write x del u by del x plus y del u over del y is equal to nu. So this is equation 1. Now differentiating this equation 1 partially with respect to x, we get, so here when we are differentiating this whole equation with respect to x partially, what do we get? Again in this part we can apply the product rule. The derivative of first with respect to x gives you 1. and the second remain as such. Now you keep the first as such x dot the partial derivative of this with respect to x. It gives you the del square u over del x square. In fact, the second order partial derivative. Now here we cannot apply the product rule because here y will be treated as constant. So we keep it as such. Now the rest of the part we are differentiating it with respect to x partially. So in fact it gives you del square u over del x del y. N is constant and you differentiate u with respect to x partially. So del u by del x you can have here. Now in the same manner, when you differentiate this equation 1 partially with respect to y, we get this expression. Okay, now let us look at the expression which you wanted to prove. Here we are having del square u by del x square. With this you require x square, and del square u over del y square. With this you require y square. So here we are having this part x into del square u by del x square, and here we are having this part y into del square u over del y square. So these two terms gives you the clue what how we should proceed further. In fact, if we multiply this whole equation with x, so we'll get x square here, and when we multiply this whole equation with y, so we'll get y square here. So we will be uh, around this expression in left hand side. Some terms of these types can be obtained, and then we can proceed further. So that is why we shall multiply here with this equation 2 with x, and equation 3 throughout with y, and then add. So you can see either we can proceed in this way, but what we have done, what is done here, this part is taken on the right hand side, and this part is taken on right hand side. So in this way, what had happened, this del u by del x, here one is coefficient and here is n, so del u by del x is common, so here we are left with n minus 1 del u by del x, and similarly here we are left with n minus 1 del u over del y. So in fact, equation 4 and 5 are obtained. So what I was telling, we will do the step here. We'll multiply equation 4 with x and multiply equation 5 with y, so that here we'll get x square and we'll get here y square, and then add. So by doing so, what do we obtain? We have n minus 1 because here we have multiplied with x and here with y. So n minus 1 is outside and we are left with x del u by del x plus y del u over del y. But from equation 1, due to the Euler's theorem, this quantity is equal to nu. So in fact, we have proved that this expression in left hand side is equal to n into n minus 1 is equal to into u. So this proves this theorem. Now the example 1. If u is equal to log x4 plus y4 divided by x plus y, then show that x del u by del x plus y del u over del y equal to 3. So the expression here looks like the Euler's theorem. So first we should check the homogeneity of this function. So in fact u cannot be homogeneous here because logarithm function is in the right hand side. So let us remove the logarithm from the right hand side. So it becomes e raised to power u is equal to x4 plus y4 divided by x plus y. Now from the numerator, if we take x4 outside, and from the denominator when we take x outside, so in fact we are left with the situation 1 plus y by x4, and in the denominator, because x is common, 1 plus y by x. So in numerator there was x4 and in denominator we had x, so we are left with x power 3, x raised to power 3, and the rest of the expression is in the form of the variable y by x, in the form of the variable y by x. So we can write it as e raised to power u is equal to x cube phi of y by x, means function of y by x. So we can say that e raised to power u is a homogeneous function of degree 3. Therefore, by Euler's theorem, we can write x del by del x e raised to power u, because here e raised to power u is the homogeneous function. Similarly, y del over del y e raised to power u. So we are writing here e raised to power u. Why? Because this is the homogeneous function, not u, plus n into u. In place of u, you will write again e raised to power u. Now let us see. X is there. When you differentiate this partially with respect to x, so you get, because the derivative of e raised to power u exponential function remains the same thing, e raised to power u, and because u is the variable, so del u by del x here. Similarly, in this part, e raised to power u y del u over del y. So now e raised to power u here, e raised to power u here, and e raised to power u here, that will be cancelled out, and what we are left with is this expression. And this is what we wanted to prove, that x del u by del x plus y del u over del y equal to 3. So we have proved this. So this is the exercise. You can try based on these concepts. So in this part, the first one, in first exercise, you will see that sine u will be the homogeneous function of certain degree, and this part you will apply that theorem which we have proved, and here again you will take this tan inverse on this side. So in fact tan of u will be the homogeneous function of certain degree, and then you will apply the Euler's theorem. So consequently you will get this expression. Now from this expression you will proceed in such a way as we have proceeded in the theorem, that first you will differentiate it with respect to x partially, then differentiate the same equation partially with respect to y, and then you have to multiply the subsequent equation with x and y respectively, and then we'll add. So this kind of expression can be obtained, and the same is the procedure for the question number 6. So tan inverse you can take on this left hand side. So this is, in fact, it will become tan u as a homogeneous function of certain degree, and you will proceed like the result of theorem. So that's it about this lecture. Thank you.